Okay, good morning, everyone. So I'm so glad to see a lot of you. One of the things I'd like to mention is that you obviously know it since you're here, but I think it would be really good if you can encourage your fellow classmates who you do homework with or hang around with and who are in 16A to come to lectures, because Module 2 is known to be especially hard. Especially for people, actually both for people who don't have physics background because they're seeing this stuff for the first time, but also for the people who have physics background and think they know this. Because they think they know this, but we do it in a slightly different, more systematic way, they're much more likely to make mistakes and actually fall behind. And so it's really key to kind of stay on top of things, and the best thing to do that is to be in the lecture, discuss with your peers, and also ask me questions. If I'm asked a lot of questions, then I will tailor the material to you, right? Otherwise, you can just go on YouTube and watch last semester's lectures or the semester before that. But the key is actually that every lecture is slightly different because I'm trying to, every instructor is trying to basically adapt to what's not clear currently in the class overall. And I think that's key, that we work together to remove these kinds of things that are not really clear, that are preventing you from doing the homework well, doing the exam well, understanding the material, right? So please ask a lot of questions and encourage folks to come in, because that's how we create the culture of the class in this lecture. Otherwise, I'm just going to roll through all the material. I'm happy, and whether you know it or not, it's a different thing, right? But that's not the objective. Okay, today we're going to continue our interesting circuit that hopefully will give us some intuition into how to actually deal with a more complex model of a full 2D touchscreen. Remember what we mentioned last time is that whenever you have a real model, real thing you're trying to solve or analyze, it's sometimes, actually more often than not, really daunting to look at all the little details in that physical thing and trying to model them all at once. Because not all these little details contribute equally to the functionality of that thing, right? So the key engineering skill is starting from very simple models and quickly recognizing what are the key components or key features of that physical thing that give you the desired behavior in your model. And then you just model that, and then the analysis becomes very simple. So you arrive, we call that most significant bits of information, right? So something may have a lot of pieces of information about it, but you don't need to know all of them. You maybe need to know only a few things and already know pretty much how that thing works, right? So that's what we're trying to do here. Look at a very complex thing and then see how it can be simplified and then reasoned about, right? So that's why we kind of build this circuit. You'll see how we're going to use this intuition to later analyze a much more complex problem. All right, so we had something like this. So R1, R2, R3, R4. This node was U2. This node was U3. And then we said, we're going to label U1 here, but that's basically this whole node, right? Because it's just a wire. And then this whole node here, we're going to call 0. That's our reference. Right, and so the question last time we were looking at is what is U2 and what is U3, right? And you kind of worked together and came up with the answers. So maybe someone remembers from last lecture. What was the answer for U2? Yes? Okay, so U2 equals R3 over R1 plus R3 times Vs. That's right. So just to be clear for everyone, this is kind of a final result. The intermediate result was that U2 minus 0 equals this, right? Why is that? Well, U2 minus 0 is the voltage between these 2 points, right? And that's and this is a formula for a voltage divider. We're dividing the voltage between 0 and U1 to a voltage between 0 and U2. Right? Voltage between 0 and U1 is Vs, and this one is a fraction of it. So then U2 equals R3 over R1 plus R3 Vs. Okay. Notice we could go back again and do the full-blown circuit analysis, but we didn't do that. We recognized a pattern, right, that this is a voltage divider, and then we just apply the formula. Right? Okay, what is U3? Yes? Yeah, U3 equals R4 over R2 plus R4 times Vs. Okay, again, it was U3 minus 0, and then a voltage divider of that. The key thing here was that you guys recognized that Vs was equally applied over this branch and over this branch, because the potential on top everywhere is U1. That's just one node. And the potential on the bottom everywhere is 0, because that's just, again, a wire. It's a single node. So in terms of voltage across them, these two branches are completely independent. I could keep adding branches like this, and the middle potentials at each one of them could be separately calculated as voltage dividers. Does that make sense? Because it's always Vs applied to each one of these new things that come in. Right? In other words, if you want to think a little bit more physically about it, whichever branch I add will sink some current. The power supply Vs will happily provide all that current, because we said the definition of the power supply is it provides any current to keep the voltage at its terminals to be Vs. Right? That's the definition. Current can be infinite. That's okay. Right? So the power supply keeps essentially the voltage between these two nodes as Vs, regardless of how many branches of resistors we have. Okay? Make sense to everyone? It's kind of a key point. This is really the key point that we'll use later. So if it's not clear, please ask me. Okay. So now we're going to do just a little build-up on top of this. So let's have that R3 equals KR1 and R4 equals KR2. Okay? What is U2 and what is U3? Talk a little bit to your friends and let me know. You can introduce yourself and say, hello. Let's figure out what U2 is. Okay, any ideas? Anywhere in the back? Any ideas? What's U2? Yes? Okay, so let's just work it out, right? It's Yeah, it's correct what you said. So we were just plugging in into this formula here, KR1, that's our R3, over R1 plus, again, we substitute KR1, right, for R3 times Vs. And then R1 goes away, so we get K over 1 plus KVS, right? And then the same deal is for this one. We get KR2 over R2 plus KR2 Vs. So it's K over 1 plus K Vs. Right? So from this, we see that U2 actually equals U3. So even though these nodes, U2 and U3, are not connected in any way, just because of the ratio of the resistors in each one of these branches is the same, gives us that these potentials are the same. Right? That's actually pretty interesting. Right? As long as I can balance the resistors, I maintain the same potential. And I can keep growing, adding more branches, and this is always going to be true. Yes?
How would you go about calculating K?
Oh, K was just something that I picked arbitrary. So the question was, how do I go about calculating K, right? So let's say I pick K of 1, right? That means I put two identical resistors, R1 and R1, right? Then if I do R2 and R2, then the voltage at the middle will always be half, right? And then if I put like two R1s, then the voltage will be 1/3, right? Etc. Mm-hmm.
Question, say we have like this circuit in the lab and we were just given the potentials and we didn't know the resistance, then would we still be able to use this like format?
Okay, nice question. So the question was, hey, I'm giving a task to produce a certain voltage here, right? Certain potential with respect to ground node. How do I go about picking a resistor, right? Okay, so that is a very deep question, right? And the reason why I'm saying this, you got to connect to what we talked about last time, is the power, right, that is dissipated in the resistor in case you have a fixed voltage across it, right? If you have a fixed voltage across a resistor, the power is V squared over R, right? Then think about what your design goal would now be, right? If you pick a 1 ohm resistor, right, from a 1 volt supply, that will be 1 watt. That's kind of hot. I mean, if I pick, but it's okay. If I pick 0.01 ohm resistor, that will be 100 watts. 100 watts is kind of a very hot light bulb, right? So you can't touch it. And in fact, that amount of power in that smaller resistor would probably, even 1 watt would probably blow it up in the lab, but 100 for sure, right? And so there are these explosion matters that are very sensitive, but also just in terms of building something that has low power dissipation. As an engineer, you will get certain objectives, right? I want to build this touch screen, but I don't want it to smoke. That's one. I also don't want to use it as like a heater in the room, right? Because days in California are hot, right? So additional source of couple hundred watts of power on the wall is probably not the best idea, right? So you can work out from these constraints what are kind of the acceptable resistances that you can have, right? Now, from that analysis, it would sound like the higher the resistance, the better, right? Because I will have lower power. But as you'll see, there are some other constraints that you have, and you don't see them yet because we're just looking at DC circuits, meaning constant currents. But when things start changing, you may want to use smaller resistors to be able to get things to happen faster. And that's a topic for next few lectures. In a few lectures, we'll see that. But for now, just understanding that resistance does affect power and you may care about power is, I think, good enough. Yeah, great question. Okay, so from here, let's make the next move. So let's add a resistor. Remember, we're kind of building up bottom up from something we know, which was a voltage divider. So we then complicated it a little bit by adding another branch, right? So when we figured out, okay, things don't change. Now we're complicating that model a little bit more, and hopefully we're going to build it up to the level that we can then use that model in something useful, right? That's kind of the game plan here. Okay, so let's see what you think about this circuit. I'm keeping now these resistors having values K, R1, and K, R2, just because we just did that, right? But now I'm going to add another element. And in fact, I'm going to do it in a different color. Okay. Right. And let's label this is I element 5. Okay, we still have our U2 and U3 here. And then, okay, U1 and 0. Okay. So, there are a couple of things I can write immediately about this without sweating too much, right? So, the first thing that I can write is that V element 5 equals U3 minus U2. Right? This is purely a voltage definition, right? It's just voltage definition. Hey, voltage is the difference of two potentials. That's it, right? Then the second one is the element equation for this new element that I just put in. And again, that one just tells me that V element 5 equals I element 5 times R5. Okay? There's nothing really new here. It's just two definitions that I applied to this element. Now comes the tricky part. Okay? So just like we do in math proofs, I'm going to assume something's true, and then I'm going to prove it's true. Okay? Or you can assume something's true and then prove yourself wrong. That also works. But in this time around, we're going to prove it's correct. So the bold assumption here is going to be that V element 5 actually equals to 0. Okay? So, I'm just saying I think V element 5 is equal to 0. Let me see if it truly is equal to 0. Right? So, if I assume this is correct, right? Then let's use it back in this equation here. Say, okay, well, if V element 5 equals to 0, then what follows from the element equation? I have that I element 5 is V element 5 over R5. And if this goes to 0, then this is 0. So what this is telling us, if it's indeed true that V element 5 is 0, then there is no current flowing through R5. Right? Well, if there is no current flowing through R5, can I remove it from the circuit? Which other element have you learned about that has 0 current through it? By definition. Okay, I'm hearing a couple of things. Yes? Ideal wire. Ideal wire has potentially zero current if the rest of the circuit is giving it zero current. But it actually, by definition, has zero voltage across it. So what other element? Yes? Open circuit. Right? Open circuit, by definition, there's no current flowing through it. So I element is zero. Voltage can be whatever is set by the outside circuitry. Right? So if indeed here the element is the element current is zero, I can just pretend this is an open circuit and pull it out. Okay? Now, it is confusing to you, and the reason why you said wire is that, yeah, indeed, I started from V element 5 equals 0, so that could also be interpreted as a wire equation, right? But we actually want to do it the other way around, because I want to lead you to a circuit that you already know, right? So let's do this. We just said, so if I element 5 equals to 0, then the circuit is the same as the one we already analyzed without R5. So let's just draw that one out real quick, just to compare and contrast. So all I'm saying is essentially this. I keep this I element 5. Okay. So what I did, I pulled out resistor 5. These two circuits still need to be equivalent. In what sense? They need to have the same U2 and U3. Right? And all the other things, currents through the branches, elements, everything has to be the same, so that these two circuits are equivalent. We're going to talk a lot more about the concept of equivalence later, but essentially, when voltages and currents are the same, circuits are equivalent. Okay. So let's see what happens here. I pulled this resistor out. Nothing should change. Right? So in this open circuit, I element 5 is a 0. That's the same that's happening here. Right? Well, if I element 5 is a 0, and you have a circuit like this is 0, U1. What do you know already is the answer for U2? What is U2? K over 1 plus KVS. What is U3? The same. Well, okay, if U3 is equal to U2, what is V element 5? Voltage. Yeah, or more formally, it's U3 minus U2, and that equals to 0. Does this make sense? So, we started from I element 5 equals 0, and we derived that in that case, indeed, V element 5 is 0. Right? So, that means that in this case, my assumption was correct. Yes?
Is this also assuming that your resistance is non-zero? Because you get zero voltage from having zero resistance and infinite?
You're right. So the question was, couldn't I just, if I had R5 be 0, then I'm of course, U2 equals U3, right? And that's true. But we want to create a model where we have a true non-zero R5. Right? And show you that as long as these resistances are proportional, even if you have the real resistor across, the voltage, the nodes are still at the same potential. Does that make sense? That's kind of the big conclusion here. Right? And the reason why we want this real R5 here is because we're building up toward this bigger, more complex model that will reflect how the touchscreen really looks like. Right, so then, when we look at how touchscreen will look like, you're going to go, oh, I know that circuit. It exhibits this kind of behavior, right? And the behavior, like the macro behavior, is that, hey, as long as these resistances are in the same proportion, regardless of the resistance across, the nodes are at the same potential. Right? Questions? Yes? Two Ks must be the same. That's correct. Because otherwise, you're creating a different value of a different value of U2 and U3, and then there is a voltage difference, potential difference. There's voltage across the resistor. The current flows. Okay. Any other questions? This is a tricky one. Okay, I have to admit. Later, next lecture, we're going to actually teach you formal equivalence and superposition techniques that will help you analyze circuits like this much more easily. But right now I don't have that tool, so I need to give you kind of this workaround. Right? Make sense? Okay, good. So now that we have the model, we're going to go and sketch out the touch screen. Okay, so let's put my artistic skills to test here. Okay, so this is going to be our top sheet. And just like we did with 1D touchscreen, there was like a red thing, which was a top conductor. Now, in this case, I'm just drawing a whole sheet, like a whole screen, right? And then underneath it, we're going to draw another one, which is our backplane. Now, there is a little like dotted thing here. This is just like trying to illustrate that this sheet is going underneath the top sheet, right? And there are some properties that we're going to assume here that are going to make, in fact, they're done like that, but like that are going to make our modeling easier. So this shaded region that I drew on top, that's like a really good conductor. I can model that as a wire, right, in our model. So this thing here is a good conductor. Or, in other words, low rho material. Okay? By the way, this is a top view. Right? The side view still stays the same. If we push with a finger, it's going to be something like this. So this is side view. Right. Okay, so this part of the red sheet, I mean the rest, the screen itself, is actually it's actually a poor conductor. High rho material. So this one we're going to model as wires. This one model as Rs. That's basically what that means, right? If it's relatively poor conductor, we're going to consider it a resistor. If it's a really good conductor, we're going to assume it's a wire, just to simplify the model. Question? Yes? Can you repeat the question? Oh, you mean on the exam? I think on the exam we'll be more specific and tell you model this as this or model this as that, right? I'm just saying here this is kind of a clarification, right? But I think as an engineer you will have to figure out when to make appropriate approximations. And just like if you remember last lecture when we did a 1D, we first did a model 1 where we treated even the backplane as a wire, right? And then we later added resistance just to see that it actually doesn't matter. But you can progressively keep adding the complexity until the model makes sense, right? Okay, so the way we're going to do this, and actually let me draw the finger somewhere. So this is a finger that's touching. The way we did this in the past is we added something to this circuit so we're able to measure voltage, right? Something that creates voltage in the circuit. What was that? This on its own cannot do anything. I need to add something to make it work. What is that? Power source, great. And where did we add the power source? Okay, to the side. Okay, in that case, in the 1D case, it was kind of looking at the side, right? But to which sheet did we add it? To the red one, right? So let me just draw the side view because that's a more familiar view for you. Right? It was something like this, yes. And then we said, okay, this was a 0, right? And then we used the backplane, which is the blue material, and we said, I'm going to measure voltage between this point and here. Let's say this is U1, right? And this voltage here was U mid potential. So we proved that U1 actually equals U mid. So if I measure U1 here always at the edge, I will always get my middle potential, right? So that was all good for 1D case. But this thing on the left looks a lot more complex, right? So let me add that source. So Vs. And let's see how can we model this now to be able to leverage some of the insights we had in the circuits we did today. So at this point, you kind of have to believe me a little bit. So it's a little leap of faith, like just like this much. If I take scissors, right, and I cut this sheet into very thin horizontal stripes. In fact, you could almost imagine it's created like that. It's not like one uniform sheet. It's just weaved in, like a whole bunch of little threads, right? And I'm just going to draw 3, but imagine there's a million of them, right? So let's say there is one thread that goes straight down from the top, and I'm drawing them as green. They're obviously red, right? So there's one here. Let's say there is one here, and there is one here, right? They're all going down from the top red electrode to the bottom red electrode. Okay. So these are conductive strings, right? Relatively poor conductor. So let's see if I can model that. If I can model that, then I'll generalize to the whole sheet. Right? And you'll see that it actually works out. Does that make sense? That's the game plan. So let's kind of try to draw what happens in that case. So I have my minus Vs. I come to here, and now I model this whole piece as a wire, right? We said that we're going to do that because it's a good conductor. So I'm just going to have that piece as a wire. Now, what hangs off of the wire vertically down? What do people think? Yeah, it's effectively a resistor, right? This thread has some resistance, but the way I'm going to model it is actually as two resistors, right? I'm going to assume that there is some virtual horizontal line here where the finger is, right? And I'm just going to say, assume I know what that length is. I don't know it, but just like we did in previous 1D case, I'm going to assume I know that length, right? So I'm just going to draw first that resistor here, and in our modeling we call that R rest, right? And then there was R touch. So this piece over here is, let's label it as, L rest. And then this piece here is L touch. Right? Does that make sense? I'm just assuming I know where the finger is. The distance between the finger and the top electrodes is all L rest. The distance between the finger position, vertical position, and the bottom is L touch. And I'm going to assign those values to these two resistors. Okay? And then I go to the middle thread. So I'm going to label this as vertical because of something we're going to see shortly. Okay. Now, in the middle thread, what do I have? Is the middle thread any different than the one I already did? It's the same, right? So I can just do the same thing. R rest vertical, R touch vertical. And then the third, same. Okay, so let's call this potential here U left. I stayed, you left. This one is U mid. And this one is we're right. Okay. What exists between these two? Between U left and U mid? These are two potentials, and there's like a conductive sheet, poorly conductive sheet in between. Yes? Some resistance, right? So let's just label that resistor. RH1. And then here, there is another one, RH2. But even ignoring this circuit over here, what does this circuit that's left, what does that remind you of? Is that a familiar circuit? Where did you see that circuit? A few minutes ago. So what's the answer? Yes?
Called an interesting circuit? Like, what is it called?
It's called an interesting circuit. It's actually, you could view this as a bridge. It's also called a bridge because this is a bridge resistor. And, these two resistors are on the same potential as well as these two. So Maybe in the homework you'll see something like this with a resistor across. Those are called bridge circuits in general. But we just call them here an interesting circuit. So this is our interesting circuit, right? So what is the answer? You see this circuit, you see the values of the resistors. What can you immediately tell me about U left and U mid? They're the same. And then, does it matter that there's a third branch? No. What is U mid and U right? Same, right? So, this is our interesting circuit. Right? So then, from this, U mid equals U left equals U right. And what is U mid then? What's the value of U mid? Yes? Okay, I can calculate U left or U mid or U right, right? So what's the value?
So it would be R touch divided by R red plus R touch times V1
Yes, times this voltage across, right? Vs. Okay. Okay, so I'm just going to label this a little bit as U mid V. And let's write it out. U mid V equals, this is rho times L touch V over A over rho times L rest V over A plus rho times L touch V over A. All these go away. So this is just L touch V over, I'll just write this as L vertical. Okay? So this is vertical. Right? This tells me where the finger is vertically on the screen. Does it tell me what's the horizontal position of the finger? No. It can be, in fact, all of these points across this one line, across this horizontal line. We just proved that all the potentials are equal, right? So we just proved that there's no way for me to know from this one measurement where the finger is horizontally. All of these potentials are going to be the same. So, what does that tell you about what we need to do next? Yes? Okay, so the suggestion is we have two electrodes, we just powered up one and measured on the other. Why don't we flip things around? And instead of applying the voltage vertically and measuring horizontally, we actually apply the voltage horizontally and measure vertically, right? It's symmetric, right? Okay, so that's actually a really good suggestion. So let's try to do that. Okay. So the question was, how do we determine the horizontal position, right? So I'm going to, again, draw the screen so we see what's going on. We can make a model out of it, and hopefully we can build or arrive to a solution faster because we've already analyzed that type of circuit. Right? So let's say this is our screen. And let's say, our finger was somewhere here, right? So, previously we applied voltage on the red. Supply was connected to the red electrodes. Now we're going to apply the supply to the blue. Right, so we're going to just do something like this. And now we're just measuring between, let's say this was our node 0, between this node and the reference electrode, right, the red electrode. Okay. Again, I can draw this dotted line, that's one string that I have, and I can pick off, let's say, another string somewhere here, and another string somewhere here. And again, there is this vertical line. It's along the vertical axis, but at the same horizontal coordinate where the finger is, right? That's going to be our bridge resistors. So let's now draw a model of that, right? I'm going to draw it as it's oriented like this, so that you're not confused about rotation, and then we're going to figure out how the two circuits are equivalent. So we have the supply, that's the same, right? And then I'm going to draw first the top, what's happening with the top wire, this one over here, green, right? So there's going to be a resistor. There is going to be U up. So, again, there is... Actually, let me just use a different color. This is L touch horizontal. This is going to be... up until... it's up. It's the blue now. Okay, and then goes up to here. So L rest horizontal. So the arrows go between the full length of the blue electrode. Okay, so this is L touch horizontal, L rest horizontal, and then the second blue string where the finger is, I'm going to do the same thing. So this is going to be L touch horizontal, L rest horizontal. Now this is U middle horizontal. And then I'm going to have another branch, that's the bottom red, green. Okay, so now along these red dotted line are the resistors, and we're going to just call them our vertical resistors. RV1, RV2. Okay, does this circuit on the right look familiar? Yeah. Okay, I'm just going to kind of try to show both of these circuits, right? I just rotated one, And okay, it's kind of like a mirror image of it, like the supply. But you see there are horizontal resistors. The vertical resistors are all proportional, right? Let me just write these actually as resistors. R. Right? So it's basically the same circuit, right? Okay, great. So if it is the same circuit, what can we say about the voltage, the potentials? What is U up equal to? How are U up, U down, and U middle related? Equal. Yep. U down. Okay. And what is U mid horizontal then equal to? Okay. R touch horizontal over R rest horizontal plus R touch times Vs. Okay. And now we can just write out the resistances. It's going to come out to be L touch horizontal over L horizontal times Vs. This is our horizontal information. Does this make sense? Yes. Oh, okay. So the question was, why did we choose to model the plate as 3 wires? Well, wouldn't it work as a single wire? Well, there is in actuality an infinite number of these resistors, right? They're all like, it's all a sheet, right? And so we chose to approximate the sheet, like the nearest approximation to the sheet is a lot of wires in parallel, so to speak, right? A lot of strips. And somehow they're also horizontally connected, right? In fact, during their whole length. So we tried to somehow approximate that, and 3 is not enough, but what we did previously with an interesting circuit, we said, we proved that I can keep adding these branches ad nauseum, right? And the result will still be the same. So starting from this, we can say, well, I started with 3, but I can make a more complete model by adding million of them. And now it's going to be a full resistor mesh, right? And the result, I know the result is still the same. I know because I know what's happening with these 3, right? Or 2. Yeah. But you kind of have to be able to claim that nothing really changes as you add a lot more elements, because that's what converges toward what's actually physically happening, right? Yeah, good question. Yes? Oh, so the question is there a linear relationship between resistance and length? Yeah, so just for a resistor as a piece of material, right, there will be linear proportion to length and inverse proportion to the cross-sectional area, right? And we're using that fact here. In fact, that's what we did. That's what this derivation was about, right? Each resistor is replaced with its physical model, which ties it to the length, right? And then we can do that. Okay? Yes? So we're trying to, so touchscreen is a sheet, right? and we try to somehow approximate it with with a bunch of discrete resistors, right? To do that, we have to make some approximations, and the first approximation is let's cut the sheet into a lot of small little strips, right? And then a small little strip, let's say, if I take a strip of material, this is, let's call it dW. This is like a super small width, right? And let's call this some height h, right? So then my area is dW times h. My length is let's say length vertical. This is the full length height of the screen, right? That's this. Right. Then the resistance of this, let's call it dr, right, will be rho times LV over A, right? And would be rho times LV over dW times H. Make sense? And I can do that for million of them. I get kind of an approximation of the whole sheet. And then, but because now I'm treating them as each as a separate one, I need to add some resistors in between, right? That give me a model of how each strip talks to each other, right? Okay. In the lab, you're actually going to be building a resistive touchscreen out of discrete resistors. So you're using very much a model like the interesting circuit. So it's kind of going to be cleaner to understand how the voltage dividers work and things like that. Okay? Okay, so instead of starting the new equivalence thing, I kind of wanted to give you guys, I don't know, I may hate myself for this, but I heard a lot of you are tired of writing a lot of equations about circuits, like big matrices and stuff. So I'm going to give you a shortcut. And this is kind of like one of these things that I give you a shortcut. It's a really neat tool, and we're going to use it as more and more as we go along. But if you're ever confused with what this does, you can always fall back to the full-blown analysis. Right? But I just want to give you something that's kind of a quick back-on-the-envelope way to do things. And it's not that much. We're going to kind of derive it from what we already know is our 7-step procedure. So it's not something totally different. I just want to be able to show you how you can do things faster. But please don't use it if you're uncomfortable, if it's always fall back to the 7-step procedure until you get comfortable with things, right? So this is a faster circuit analysis. Right, and I guess we can use let's use our friend interesting circuit just to illustrate the point. No, actually this is R2, this is R3. I'm going to just write it out as I don't know that these resistors are in proportion. Just some circuit that looks like this. Right. So notice, even without spelling it out, I kind of already labeled the nodes. Right. I labeled 1, 0, U1, U2, U3. Right. That's kind of already something we've done in the 7-step procedure. Right. The idea was label the nodes. Pick one to be the reference node, label the others. So that's the same. So the first step is label the nodes. Nodes, unknowns. and the reference node. Right? Okay. So the second step is if there are nodes that are directly where the voltage source is in between the two nodes, I can immediately write that out. Right? So step 2, write equations for nodes that have voltage sources between them. Why is this? Well, that's already that's already kind of solving your problem, right? In this case, I write U1 minus 0 equals Vs, right? That's it. It's done. So from here, I know that U1 equals Vs. That's one less variable in my circuit, right? Step 3, I'm going to write KCLs, but I'm going to write KCLs, I'm going to write a KCL and IR element sandwich. Okay, how does that look like? KCL and IR element combo, including any possible current sources. All right, what is he talking about? You remember, in a 7-step procedure, we would just write KCLs. We would have to label all the currents, write all the current equations, then separately write out the element equations, V equals I times R, and then we substitute V's as U's, etc., and then we form these bigger matrices. Well, I can do a shortcut. Let's say pick some element. Let's say this element R1. If I label this current as I1, coming out of node U2 through R1, what can I write about this current? Well, that current is equal to U2 minus U1 over R1. Right? What I've done here, I've kind of done two equations in my head. Okay? First equation was, what I skipped was I said, there is this voltage V element 1, because I labeled the current arbitrarily. Now I have to use a passive sign convention for V element 1, right? So I have to orient the plus this way. So then I can say V element 1 is equal to I1 R1. The second equation, so this is element definition. The second equation that I did in my head was that V element 1 is U2 minus U3. This is voltage definition. So if you got tired of writing these two over and over again for every element, then this is the shortcut, right? Sorry, U2, so this is U2 minus U1. Okay, someone trying to keep you honest. Okay, so U2 minus U1. So you see, this is V element 1, right? Does that make sense? If it's confusing, spell it out. Let me know. Questions? All we did is we used these element definition and voltage definition, right? So V element 1 is U2 minus U1. That's the voltage across here. And we're calculating I1 as voltage over R1. For that, we're using this element definition here, Ohm's law. Does that make sense? Okay, so now this is kind of like a pattern. Right? The current out of the node through the resistor is equal to the volt potential difference between that node and wherever the other node is over the resistor value. So what I can do now is I can write KCL for this node U2 right out of as these elements. So let's see the magic. So this is the magic. Magic is this current up is, we already did it. It's U2 minus U1 over R1. Plus, this current down is what? Let's see who's picking up. How do I write this current down? Yes? Yeah, U2 minus 0 over R3. Plus this current over here. What is that?
U2 minus U3.
Exactly. U2 minus U3 over R5. And equals to what? 0. Bingo. Jackpot. See how simple this is? I don't have currents as variables. I have a minimum number of unknowns, which are just my unknown potentials. I already cleared U1, so that's out of the picture. I can replace it here with Vs, right? So I only have two unknowns. That's U2 and U3. Right? So this one we already know is Vs from here. Right? Okay, so I have two unknowns, U2 and U3. What else do I need to do? Yes? Yeah, so let's apply this magic on the other node, right? U3. So applying to U2. And now apply to U3. Okay? So let's see how this one goes. Let's do it. Now, notice what I was doing here. Just to make my life easier, I picked the currents always going out of the node so that I can write I always start with U2. So I'm obeying the passive sign convention, right? So everything's working out. So here, what I'm going to write for this current up. For this current up, what can I write? What's the ratio? Yes, U3 minus U1 over R2. So it's U3 minus U1 over R2. Like if you're a visual type, I pick a node, imagine I pull it up, and I'm looking at currents flowing down from that node, like down a mountain, right? And I'm just doing that node potential minus wherever the current's going over the resistors on that path. Right? That's kind of the visual thing. That's kind of like when Neo looks through the code, he sees stuff. That's kind of that thing. Okay, so this current, what do I write for that? U3 minus U2 over R5. Okay? Notice that's the same as this expression over here, just the opposite sign. And obviously it's the opposite sign because these two currents are kind of showing in the opposite direction on the same element. Plus the last one is down. What is that? Yeah, U3 minus 0 over R4. Okay? So now we can again go here and apply Vs, right? And we can then tidy this up a little bit. So you get U2 times 1 over R1 plus 1 over R3 plus 1 over R5 minus 1 over R5 U3 equals Vs over R1. And then this one over here is U3 times 1 over R2 plus 1 over R5 plus 1 over R4. Actually, I should have written U2 is here present as well. So let's do it like U2 times minus 1 over R5 plus this equals Vs over R2. Okay? This is just a 2x2 matrix, right? And I solve it for U2 and U3. Or I can just do substitution here, whatever is your favorite method, right? So I don't know if you find this easier or not, but it is going to be a faster method because you don't have to identify all these intermediate variables. Element voltages, element currents, it's all kind of implicit here, right? But it's like driving a Ferrari, right? You have to, or, some comparable vehicle of that class, like maybe, Tesla Roadster, or the newest ones. Like the point is, be careful, because just like we did here, there's like 2 or 3 equations that you have to do in your head to jump from our 7-step analysis to this. The benefit is I only have 2 equations, I'm done. Right? And you have 18 equations, which will become 9 equations. Actually, you have 27 equations, which will become 9 equations, which you put in a matrix. Right? So I suggest you practice this somewhat and see how comfortable you are with it. If you get very comfortable, you can be blazingly fast in analyzing circuits. That's the benefit, but you need to put in a little bit of effort to kind of do it. And in fact, when circuits only have a few nodes, like when we go to op-amps and stuff later, this is going to be very handy to analyze, like if you can master this skill. But we're not expecting you, this to always follow this routine. If you're uncomfortable, always fall back to 7-step procedure. It's fine. It's just more work for you writing stuff out, but it's definitely going to give you the right answer. Does that make sense? Okay. Any more questions? Yes?
So when we're applying the magic key to the nodes, can we just assign the currents to an element in a different direction?
Oh, absolutely perfect question. So the question was, hey, what if I want to assign currents in a little bit different direction here, right? So, what I could tell you off the hand is like, okay, just the sign changes, but actually let's do that as a quick example so that you see it's not a big deal. As long as you're careful, okay? And I'll show you what careful means. Yes?
Why do we have
2 currents going through R5. Well, remember in this magic procedure, what we did was we were trying to do KCL on each of the nodes, right? So I'm only interested in the currents that are related to that node. And yes, if they end up flowing through the same element but from 2 different sides, that's fine. I don't care. Right? I only care about the KCL around that node, and I'm writing that equation in the most convenient way. Here, the most convenient way for me was that, notice, if each current is going out of the node, all my parts of the equation have U2 with a positive sign. So it's very easy for me to check whether I did my math correctly, right? I just look at this and say, oh yeah, second one was about U3. U3 is always first. So that's easy, right? Okay, so what if you want to do it slightly differently? Let's say I'm just going to draw this one node, R1. So there's U1 here, R3, there is 0 here, R5, we're doing U2, and there's U3 here, right? Okay, so let's say I want to do something like this, where I changed my top to go in, right? Fine, I'll just write that equation. I'll write the bottom two stay the same, so they're essentially going to be U2 minus 0 over R3 plus U2 minus U3 over R5 equals 0. But then I have to write minus, because remember, what comes in must come out, right? So the sum of these two currents has to be equal this other one. And if I move that current on the left side, I get a minus in front of that current. So it's minus this current. But this current is defined as U1 minus U2 over R1. Right? I have to obey the passive sign convention. So guess what happens? I get the same thing. Right? I just have to, it's just a headache of a minus on a minus, right? So this is the same as U2 minus U1 over R1. So nothing changed. Right? What changes is if you're inconsistent here and you write that this current is U2 minus U1. That's a mistake because it breaks the passive sign convention. Right? So as long as you're consistent, you're using passive sign convention, you can write this KCL however you want. My suggestion was the easiest magic is with just pick that node and make it the first element in every term, and you're never going to have a problem, right? Does that make sense? Yes? Can you repeat that? I'm not quite sure. Oh, so I think the question was like, I kind of eliminated U1 up front, right? And actually, in more complex circuits, it's not going to be always that the supply is between the the 0 and some node. That will give you an extra equation that's going to tie two potentials together. So you will use it later in the system of equations, but it's easier. And one more thing, just to give you an example, is that let's say in this example here, I had a current source coming in. Let's say I had a current source coming in. Right? Well, what that means to this KCL, I would just directly write it. So I would say, this is coming in, so it's minus IS1 minus this rest. Right? So you just directly add a current source. And you don't have to do any of the extra equations. Okay. Thank you.